Okay, so what we have done is we have shown there exists such a map. What about uniqueness? Well, uniqueness is easy. Yes, well, it suffices to show, again by using compositions, show that if phi mapping suppose phi maps, of course, H to H isometry such that it sends the triple 0 1 infinity to 0 1 infinity, then phi actually is equal to the identity. Well, I mean, this is really easy to see. First of all, there is a small subtlety. Phi preserves cyclic order on boundary H, which is boundary D. Okay, why is this? What do I mean by this? I have 3 points which I am going to call 0 1 infinity. Okay, these correspond to 0 1 infinity. Well, going from 0 to 1 to infinity is going counterclockwise, and what you know is that phi is phi mapping S1 infinity to S1 infinity is a homeomorphism. Okay, and if it takes 3 points to themselves, then it takes the counterclockwise direction to the counterclockwise direction. So it has to be either orientation preserving or orientation reversing. Because it's a homeomorphism, it has to be orientation preserving. Okay, so this implies that phi maps Z to AZ plus B by CZ plus D. So I have not written down a formula if it's not a fractional linear transformation but orientation reversing, but we know it's orientation preserving. So we have already deduced that it's a fractional linear transformation. These are all the isometries of hyperbolic space. Yeah, we didn't actually prove this, we proved the other way around, but it's an easy exercise to prove this. And so what we deduce from this is now, so 0 maps to 0, sorry, infinity maps to infinity first, implies, well, there's no denominator, phi maps Z to AZ plus B, and 0 maps to 0 and 1 maps to 1 implies that in fact phi maps Z to Z. Because the image of 0 is B, that should be 0, and the image of 1 is A. Once you know that image of 0 is B, so you're once you know B is 0, so you're done. Okay, so we've seen that the group of isometries has a very nice description in terms of boundary. Given any 3 points and any other 3 points, there's a unique isometry which takes one to the other. Okay, so we look at one more aspect of infinity, which is what we would call ideal triangles, which is extremely important in many contexts in hyperbolic geometry and its applications. Okay, but I want to say one thing about that which follows from what we just observed. So what are ideal triangles? These are triangles with all vertices at infinity. Okay, so let me take 3 points at infinity, P, Q, and R. Okay, and then there are geodesics that join them. Incidentally, one thing we'll see which we'll use later is, remember that both these geodesics are perpendicular to this line. So each of these angles is actually 0. So this is a curious object. It has all its vertices at infinity, even though there are 3 geodesics. There's no Euclidean analog of this. All its angles are 0. Well, the corollary to our theorem is that all ideal triangles are congruent. Now, congruent means isometric. Actually, it means more than that. It means there's an isometry of the whole space, the hyperbolic space, which takes one triangle to the other. In particular, it restricts to an isometry of these. This is an immediate consequence of the 3 transitivity. Okay. In fact, 3 transitivity says that there is a unique isometry which takes one hyperbolic triangle to the other.